Good day to everyone, especially to you, Engineer Laios. We are the Group 2 and we have conducted a feasibility study entitled Assessing Flood Early Warning Systems Using Flood Models for Pasig Marikina Basin, a non-structural approach to hydrology. So as we all know, flooding in Metropolitan Manila is a persistent issue due to heavy rainfall from the Pasig Marikina River, causing varying flood intensities. So to address this, non-structural measures like land use planning, watershed management, flood forecasting, early warning systems, and community-based disaster risk reduction will be analyzed or being considered. So we have listed the objective for the study. First is to simulate flood propagation along the upper Marikina River using the flow model. The next is to calibrate and validate the HBB model in Pasig Marikina River Basin. Next is to develop a variety of flood prevention strategies for the Pasig Marikina River Basin based on the findings and modeling outcomes. So lastly is to perform a thorough evaluation of the hydrological situation in the Pasig Marikina River Basin, which involves examining historical precipitation trends, river flow records, groundwater levels, and of course, previous instances of flooding, which can be used as part of the solution for early warning systems in this specific area.
My name is Jeanine Carla Fernando and I will be discussing the scope and limitation of the study. So the scope of our study is it aims to simulate river flow, rainfall, and other factors contributing to flooding in the Mangahan floodway. It analyzes historical rainfall patterns, flood events, and flood-prone areas in the Pasig River Basin, and it develops a model for flood control activities without implementing actual mitigation strategies. And the limitation of our study it only focuses on the Pasig River Basin, excluding environmental impact assessment, and its accuracy depends on historical data and information, with long-term environmental changes potentially affecting its comprehensiveness. Research questions. The first question is, how accurately can the Montalban water level gauging station discharge be simulated using the HBV semi-distributed model? The second question is, can the Upper Marikina River flood wave propagation be accurately simulated by a Duflo model? And the third one, what factors influence the reliability of HBV and Duflo models in predicting flooding, and how can these models be improved for effective early warnings? And the last question is, how can non-structural models be customized for Mangahan floodways' unique characteristics to enhance flood prediction precision?
For the solution, due to the persistent issue of flooding in the Pasig Marikina Basin, experimental pilot will be used to evaluate non-structural approaches in mitigating the inherent effects of flooding in the area. Hydrological modeling and data analysis such as the flow and HBV model are used to evaluate and improve innovative flood prevention solutions. Research gaps addressing the region's specific climate resilience needs. Existing studies tend to focus on generic flood mitigation strategies that fails to consider the climate condition, like monsoonal rains and typhoon that plays an important role. Next is the insufficient emphasis on community engagement and capacity building. Many studies fail to acknowledge the importance of involving communities in flood mitigation initiatives. Third is the lack of emphasis in ecosystem-based techniques. Current studies do not adequately explore tactics such as wetland restoration, reforestation, suitable land use planning. And lastly is the technology in flood controlling research is understudied, since given the advancement in technology, there exists an untapped opportunity to enhance the accuracy and timeliness of the forecasting and monitoring.
For the methods of research, we use mathematical, computational, and simulation techniques to understand the behavior of the hydrological system in the basin. It is primarily focused on the use of two flood models, which is the HBV and Duflo model, as it enables the effective evaluation of the hydrological situation and to the development of flood prevention techniques. The research local, it is simply conducted in the Pasig Marikina River Basin, which is situated on the eastern portion of the Manila Metropolitan Region in the Philippines.
Hello everyone, I am Yala Crishay Escampo, and for our research study entitled Assessing Flood Early Warning Systems Using Flood Models for Pasig Marikina River Basin, a Non-Structural Approach to Hydrology. In my part, the study uses sources of data to finish the study. The research studies are based on previous studies such as their observation and experimentation. The experiments have been analyzing two or more independent variables and its resulting effects on independent variables of interest, likely to conduct a cause and effect linkages for the scientific studies of regular utilization. The academic research used two categories to gather data. One is the primary data and the second one is the secondary data. For our primary sources of data in flood modeling for the Pasig Marikina River Basin, we use topographic maps, river flow measurements, rainfall data, land use information, soil types, and historical flood models. These data set us help estimate and predict potential flood scenarios in the area. For the secondary sources of data in flood modeling, for the Pasig Marikina River Basin study, we encompasses satellite imagery, aerial photographs, hydrological models developed by researchers or organizations, government reports on infrastructures. Also, we have urban development for our secondary data, as well as the academic papers and studies related to hydrology, climate, or similar flood modeling in other regions. This secondary data can complement primary data and provide additional insights for comprehensive flood modeling study. The study used two models, the HBV semi-distributed model and the Duflo model. As we can recall, HBV model stands for Hydrologiska Bryan's Vattenbalansavdelning, which stands for Hydrological Water Balance Department. This HBV model was used as hydrological transport model and first used in the Scandinavia. HBV model used computer simulation to analyze river discharge and water pollution. While Duflo model stands for Dutch Flow Model and first used by the Dutch Water Board for simulating one-dimensional unsteady flow. Another inclusion for our sources of data of our study are the critical procedures and formulation for the following. 1. Sustainable flood mitigation strategy for the Pasig River Basin. This is used to extracted parameters and it was derived from digital elevation model. It was sourced by nearest global dataset and it was obtained in the Shuttle Radar Topographic Mission or what we call SRTM. Second critical procedure, which Integrated Land and Water Information System, or ILWIS, stands for ILWIS, are used to derive catchment from the digital elevation model. Third procedure is precipitation and water level data, which are obtained from the EFCOS database, or what we call FCOS database. Fourth procedures are comprehensive collection of 9 cross-section, which are surveyed in the fieldworks. They surveyed using a complete station instrument, which are provided by Pag-asa's flood forecasting branch. As a result, the researchers methodically sorted and categorized the data collected during the study in accordance with the research design and created research questions.
This slide is all about data gathering procedures for the HBV model, involve collecting various types of information. First, collect precipitation data for the watershed. Second, gather temperature data for the same watershed. Third, obtain potential evapotranspiration data. Fourth, collect information about land use and land cover within the watershed. Fifth, collect topographic data, including elevation and slope information. Sixth, collect historical stream flow data for the watershed. And seventh, calibration of the HBV model parameters using historical data for accurate simulation of observed hydrological processes. And the last, Validate the HBV model with independent data to ensure its accuracy beyond the calibration
The
dataset.
data gathering process for the DoFlow model is a comprehensive procedure aimed at acquiring diverse information crucial for informing the model's parameters and establishing accurate boundary conditions. This involves several key steps. To begin with, detailed topographical and river network data are meticulously collected. This foundational information is vital for ensuring a precise representation of the physical environment within the model. Historical meteorological data is then gathered, providing essential insights into past weather conditions. This data is crucial for simulating realistic scenarios within the DoFlow model. River flow data from gauging stations is acquired to incorporate real-world measurements into the model. This information helps in accurately reflecting the flow dynamics of the studied rivers. Clear specification of boundary conditions is a critical step, defining the limits and constraints within which the DoFlow model operates. Data for initial conditions is obtained, offering a starting point for the model simulations. This information establishes the baseline for the dynamic processes the model will simulate. Information on land use patterns is collected, enriching the model with insights into the human impact on the studied area. The calibration and validation of the model involve using dedicated data for verification. Quality checks and controls are implemented to ensure the accuracy and reliability of the gathered information. Subsequently, the collected data is meticulously prepared for input into the DoFlow model, a crucial step to ensure seamless integration and accurate representation within the simulation. Finally, the integrated data becomes an integral part of the DoFlow model, facilitating the creation of robust simulations that reflect the real-world conditions of the studied system.
The DoFlow model stands out in the realm of hydrological and hydraulic modeling due to its sophisticated approach in handling complex fluid equations. Its core strength lies in employing numerical methods to simulate and predict the behavior of water in rivers, channels, and other hydraulic systems. This software is crucial in various domains including urban drainage design, flood risk assessment, river management, and water resource planning. Overall, the DoFlow model's strength lies in its comprehensive approach to modeling fluid flow, utilizing numerical methods and real-time data integration to simulate and predict complex hydraulic systems with precision and accuracy.
HBV model. Its purpose is to mimic the flow of water depending on precipitation via watershed. Monthly evapotranspiration estimations, stream flow records for calibration, and shorter time-step precipitation records are examples of input.
For the conceptual paradigm, study focuses on the Pasig River Basin as the main area of interest. Input parameters include the Pasig River Basin, hydrological modeling technique, hydrometeorological data, review of related literature, and the hydrological cycle. For the hydrological modeling, two techniques were used, the DoFlow and the HBV. DoFlow was used for dynamic flow computations in open water systems and intricate water quality processes. HBV was used for simulating continuous runoff with semi-distributed features. Initial parameters for both techniques require hydrological data of the Pasig River Basin. Data requirements include the hydrological data, precipitation, river discharge, weather patterns, and historical flood records. Geographical information system was also used to understand landscape impact on water flow and identify flood-prone areas. Infrastructure details like levees for dams and drainage systems are crucial for efficiency evaluation and identification of areas that are needing improvements. Related literature serves as the basis and supporting studies for the research. The hydrological cycle was used as a theoretical basis, specifically the runoff process. Runoff data is crucial for enhancing the understanding of watershed and river system functions. Precipitation is a primary meteorological factor driving runoff. An HBV model represents precipitation in the form of snow or rain, which is based on temperature thresholds. Soil moisture accounting procedure in the HBV model significantly influences runoff because soil moisture influences percolation. Boundary conditions are key inputs in hydraulic models. In Duflo framework, physical boundaries can be defined as fixed values or time-varying data for water level or river discharge. For the model calibration, it involves adjusting parameters, primarily the surface runoff roughness coefficient, to minimize disparities between the observed and simulated data. It is typically done through manual intervention. For the expected results of the study, it aims to generate simulated discharge hydrographs using calibrated HBV and Duflo models. The results can be applied in flood management and early alert systems within the research area.
Shown in Figure 4.1 is the HBV model calibration result, shown as discharge hydrograph.
In the figure 4.1, the blue line represents observed discharge and the pink line represented simulated discharge, where in the y-axis are the discharge and units per seconds, and in the x-axis are the dates.
So the model has generally succeeded in replicating the timing of the hydrograph, although some discrepancies are evident at specific peaks. Notably, on December 2, 2018, there is a significant disparity, with the simulated peak at 998.7 cubic meters per second compared to the observed peak of 1,344.10 cubic meters per second, resulting in a difference of 345.4 cubic meters per second. Examining Figure 4.1 reveals specific discrepancies, such as on September 28, 2018, where the simulated peak is 806.7 cubic meters per second, while the observed peak is lower at 648.3 cubic meters per second. These variations in peak values warrant closer investigation to enhance the model's accuracy and reliability.
In a while, base flow analysis. Base flow distinction in Figure 4.1 obscured due to vertical scale limitations. Comprehensive discussion on base flow in Figure 4.2. Base flow consistently underestimated for the majority of the hydrograph during calibration. Small section at the end of the hydrograph shows overestimation extending into the initial validation period. This was shown in Figure 4.4. As you can see in Figure 4.2, or the HBV model calibration, results shown as water level, which the observed water level on its highest peaks are on September 3 and the lowest peak are on June 4, 2018. While in Figure 4.4, our HBV model validation results shown as water level hydrograph. The highest peak of the observed water level are during those between November to December, and the median peak would be on July 4 and going highest to September 4, while counting the lowest peak would be September 4 until October 4.
We will be discussing the Duflo model configuration. The Duflo model was used to simulate lateral inflows in the RAM precipitation runoff module, managing the intermediate region between Montalban and Santo Niño stations. So, according to the figure 4.5, the simulation revealed a direct correlation between area and discharge, with area 2 exhibiting the highest flow and area 3 displaying the lowest. The resulting discharge is integrated into the upper Marikina River flow.
This slide is all about hydrograph calibration and simulation. Calibration focuses on hydrograph peaks for flood control and early warning support. This approach ensured that the model accurately reflected the high points of the hydrograph, enhancing its reliability in predicting and managing flood events. As you can see from the figure, The simulated hydrograph closely matched the observed water level, with minor discrepancies. The flag lag time from Montalban to Santo Niño was 4 hours, and the R2 during the calibration was 0.91.
We're going to talk about the Duflo model, execution, and Nash-Sutcliffe efficiency. So the model was executed using an optimized parameter set and a hydrograph from the HBV simulation, achieving a Nash-Sutcliffe efficiency coefficient of 0.90. The simulation showed close alignment with the observed hydrograph, but underestimation during peak flows. The discrepancy decreased as the flow travels downstream, with the difference between the observed water level and the HBV model simulation decreasing to 0.17 meters after the Duflo simulation.
HBV takes past stream flow and meteorological data into account by modifying the model's parameters and input data. Through the optimization of the model's ability to replicate hydrological processes, the methodology ensures that flood risk and river discharge are accurately estimated.
DoFlow. It is a set of software for hydraulic and hydrological modeling. The program uses numerical techniques to resolve intricate fluid flow equations.
The study develops a non-structural approach to hydrology in order to design more effective flood mitigation techniques for the Pasig-Marikina River Basin in the Philippines through the use of two models. The factors that influence the reliability of HBV model and Duflo model in predicting flooding includes the parameter sensitivity, the data availability, and the calibration or validation procedures. For the parameter sensitivity of the HBV model, it consists of KHQ, which is the recession coefficient, the film capacity, and last is the alpha values. Whereas in Duflo model, it consists of surface roughness coefficient K, and the data availability or the data collection can be enhanced to provide more accurate input data, and for the calibration and validation procedures, it can be refined to produce or to create more detailed representations on the changing conditions within the basin.
Based on the conclusions drawn from the findings of this study, further enhancement might be made by taking into account the following recommendation. First is to utilize a more extensive time series dataset for the calibration and validation of the HBV model. Since this study uses only a dataset considering of 3 years worth of early rainfall and water level measurement. Second is to include additional assessments on environmental impacts and long-term environmental changes, since it will enhance the effectiveness of flood early warnings and achieve better results. Third is to incorporate additional reinforcestations in vicinity of catchment local. It will provide a more accurate depiction of the spatial distribution of rainfall. And lastly is rainfall estimating techniques derived from radar sensors and other satellite equipment can be valuable when longer forecast period is used.